Hey everyone, welcome to The Explainer. I am so pumped to be your guide today because we are taking that incredibly dense textbook chapter and turning it into your absolute ultimate chemistry exam study guide. I always tell my students, think of the periodic table, it's not just some flat, boring chart on a wall, right? It is a vibrant, highly organized neighborhood. Every single atom has a specific address. And depending on exactly where they live, they behave based on some really strict rules. We're talking rules about how big they get, how tightly they guard their own belongings, and, well, how aggressively they try to take from their neighbors. Okay, let's dive into our roadmap for today. We've got 4 main sections plus a bonus. We're hitting atomic and ionic radii, then the ionization energy price tag, moving into electronegativity and electron gain, followed by a super fast periodic trends summary table. And finally, we'll wrap up with some exam challenge questions. Let's get to work.
Section 1. Atomic and Ionic Radii. So our first stop in the atomic neighborhood involves essentially pulling out a tiny tape measure. We want to check the atom's waistline, just to see how much space these tiny residents actually take up. Now, the textbook gives us this very formal definition. It says atomic radius is the distance from the center of the nucleus to the outermost shell of electrons, and it throws in specific types like crystal, covalent, and van der Waals radii. But listen, let's simplify this. Don't let those technical terms freak you out. Basically, it's just a measure of how far the electron clouds reach out from that dense, heavy center of the atom. It is literally the size of the atom's personal bubble.
Now, how are we actually going to remember the size trends across the periodic table? Well, I've got a quick mnemonic to help you lock this in for exam day. Ready? Left to right, pulls them tight. I'll say it again. Left to right, pulls them tight. As you move from left to right across a period, the atomic radius decreases. Why? Well, because that increasing nuclear charge acts like a stronger and stronger magnet, pulling those outer electrons closer and closer in. But as you move down a group, you're stacking on entirely new electron shells, so naturally the radius increases. Just remember that rhyme. Left to right pulls them tight.
So what happens when an atom actually gains or loses an electron to become an ion? Well, you have to visualize the difference here. A cation, that's our positive ion, is absolutely always smaller than its parent atom. I mean, it literally lost a layer. But on the flip side, an anion, the negative ion, is always larger than its parent. It gained an electron, which adds more negative repulsion into that cloud, making the whole thing puff out. All right, rapid active recall time. Let's test that memory immediately with a pop quiz. This is pulled straight from question 13 in your textbook. How do the atomic radii change across a period? Think back to our catchy phrase, you got it. In general, atomic radii decrease on moving from left to right in a period and increase on moving down a group. Left to right pulls them tight. If your brain went right to that answer, you are exactly where you need to be.
Section 2. The ionization energy price tag.
Okay, if atomic radius was all about measuring the waistline, ionization energy is the literal price tag required to go and steal an electron away from a neighbor in our atomic neighborhood. The exact textbook definition is the amount of energy required to remove the most loosely bound electron from an isolated gaseous atom. See, elements hold on to their electrons with totally different strengths. So this value is quite literally the cost, the exact amount of energy you have to pay up just to break that grip. So what actually drives this price up or down? Well, it relies on a few key factors: the size of the atom, the nuclear charge, the screening or shielding effect from those inner electrons, penetration effects, and the atom's electronic configuration, like if it has stable or half-filled shells. But as a general rule of thumb, because atoms get smaller and hold their electrons tighter across a period, that ionization energy price tag goes up. Conversely, as you go down a group, the atoms get bigger, those outer electrons are way farther away from the nucleus, and so the energy cost to steal one just drops. Now here is something really fascinating. Think about how that price tag goes way, way up for successive electrons. When you remove that very first electron, which we call the first ionization energy, or IE1, the atom becomes a smaller, positively charged cation, right? So if you try to steal a third electron from that already positive, highly guarded ion, the cost absolutely skyrockets. The third ionization energy, IE3, is always drastically greater than the first.
Time for another rapid-fire textbook challenge to see if you caught the logic of what we just talked about. Question 16. Among IE1, IE2, and IE3 of an element, which one is the largest?
Spot on. IE3 is by far the largest.
As we just covered, stealing from an atom that is already positive is incredibly difficult. Those remaining electrons are held so tightly by the nucleus, requiring just a massive surge in energy to pull another one away.
Section 3. Electronegativity and electron gain.
All right, if ionization energy is the cost of stealing, this next concept is the great atomic tug-of-war over shared toys. Electronegativity is the tendency of an atom to attract the bonding or shared pair of electrons towards its own side in a covalent bond. Think of it exactly like a daily schoolyard tug-of-war. You have two atoms sharing a rope, and the rope is the electrons. The highly electronegative atom is simply the stronger player on the playground, pulling that shared rope much, much closer to itself. Warning, please pay close attention right now, because this is a massive, very common exam pitfall. Students mix these two up all the time. Electronegativity is about pulling a shared pair of electrons within a chemical bond. On the other hand, electron gain enthalpy is the energy change when adding an electron to an isolated gaseous atom. So, one is shared, one is isolated. Do not confuse these distinct definitions on test day. Looking at electron gain enthalpy specifically, here are the 3 absolute must-know textbook trends. Number 1, halogens have the most negative electron gain enthalpies. They are absolutely desperate for one more electron. Number 2, noble gases have large positive values. Why? Because their shells are already perfectly full. They hate adding electrons and require actual energy to force one in. And number 3, nitrogen also has a positive electron gain enthalpy because its half-filled shell is remarkably stable exactly as it is. Let's challenge your short-term memory again. Question 20 from the back of the chapter. Name the elements which possess the most negative values of electron gain enthalpy in their periods. Who are the most desperate atoms? The halogens, yes! They are just one single step away from that perfect noble gas configuration, so they happily release a ton of energy when they finally snag that electron. Keep this energy high, guys, because we are entering our final summary. Section 4, Periodic Trends Summary Table. This brilliantly illustrates literally everything we've learned today, all organized in one logical place. Go ahead and take a screenshot of this for your rapid review. Let's walk through these columns really quick. Across a period, left to right, atomic radii decrease. Remember, pulls them tight, while ionization energy and electronegativity both increase. Notice how they share that exact same directional trend. Then down a group, from top to bottom, the atomic radius increases as the atoms get bulkier, while both the ionization energy price tag and the electronegativity tug-of-war strength decrease. You see? It's all perfectly connected. Section 5, Exam Challenge Questions. You have officially made it to the final stage of our study guide. Congratulations! Now, here are some discussion prompts I highly encourage you to take to your study partners to prepare for that deeper level thinking. First, question 12. Why is the van der Waals radius of an atom greater than its covalent radius? Second, debate this concept we covered earlier. Discuss exactly why nitrogen has a positive electron gain enthalpy while halogens are negative. Go debate these exact textbook questions out loud with your groups. Trust me, it is the absolute best way to solidify your understanding. And I'm going to leave you with this final, provocative thought to ponder. Question 14. Why is a cation smaller than the parent atom? Seriously, think about what happens dynamically when you strip away an outer layer of electrons and how that nucleus reacts to having fewer electrons to pull on. Keep questioning the incredible rules of our atomic neighborhood. Best of absolute luck on your chemistry exam, and we'll see